Ophir offers a range of measurement solutions for laser power, energy, as well as beam position and size. Together with the appropriate sensors, we offer standalone meters, which can also connect to a PC, as well as PC interfaces. The PC software application that's used to communicate with and control the instruments when they're connected to a PC is our STARLAB application. STARLAB communicates with the instruments via a USB interface, or in the case of the Quasar, a Bluetooth interface. For instruments that connect to a PC via RS-232, one would use the STARCOM application instead of STARLAB. STARLAB enables the user to display measured data using various graph types, perform a wide range of functions on the data such as attenuate, density, etc., connect multiple sensors or channels in parallel, measure, log, and analyze measurement data from multiple channels simultaneously, communicate with external software systems, have maximum flexibility in how all these measurements are performed. And with all of that, STARLAB remains very intuitive and easy to use. This video is part of a set of short video segments that together form what might be considered a video STARLAB user's guide. Each segment shows how to use a particular feature or set of features of the STARLAB application. We're now going to look at how to perform basic measurements using the STARLAB application. We double-click on the STARLAB icon, and we come to the Select Devices window. Here we see a list of all the devices, sensors, and instruments that are right now connected to the PC with STARLAB running. To begin with, we'll select just one channel, one sensor. In this case, we'll use the thermopile sensor. You'll notice that the pulsar instrument is automatically selected as well. And to keep things simple, we'll choose Together. We're now in the main measurement screen. Let's have a look at what we have here. This window is the numerical readout. This is the real-time measurement of, in this case, power in units of microwatts. The main measurement parameters of the sensor are set using this window. In this case, we could choose between power and energy. With laser, we select the wavelength that we're measuring at, and here we set the range or the scale. If we were to make any changes in any of these parameters, the Save button would become active, which would allow us to save those configurations into the memory of the sensor itself. This is the graphical output. We can control the axes of the graph to make it more comfortable to use. So first of all, we can reduce the time axis down to 1 minute, just so that it moves a little bit more quickly. We set the y-axis, which represents power, to a convenient level based on what we see is the average reading that we're getting. In this case, we're going to change this to microwatts, and we can adjust the value either using the sliders or by manually typing in a number in the field over here. We're going to adjust this to a point where we get a graphical readout of the measurement in a comfortable part in the center of the screen. And now we can see that the screen is moving along. After 1 minute, one full screen is completed, and the screen then continues to scroll smoothly. Here we have statistical information about the measurement that we're performing, the minimum and maximum values that have been measured so far, their average, standard deviation, and if we've been over range at any point, the number of times that that's happened. In general, the parameters that form the configuration of the main measurement screen depend on the sensor being used. In this case, the information that appears is the information that's relevant for a thermal sensor that measures average power or single pulse energy. We can select from among a number of different graph types. Right now we're looking at a line graph. If we open that, we can change that to a bar chart, a histogram, pulse chart, or a virtual analog needle. If we select persistence, we can see a history of where that needle has been. When we deselect persistence, that disappears. We'll go back to the line graph. Here in the menu bar, we see a number of icons that are active or inactive as relevant for the measurement that's right now taking place. This icon would return us to the Select Devices window. This icon would restart the application and the devices. This icon clears the display without zeroing the devices or restarting the application. So for example, logging that might be going on would not have been affected. Other icons are not active because they're not relevant to the setup that's being used right now. We'll look at those in future video segments when we use those functions. Fully indexed help. There are also a number of advanced functions that can be used to optimize the readings. We'll have a brief look at those. Zeroing would zero the instrument, which we recommend to do on a periodic basis, typically once every other month or so. Calibrate allows the user to adjust, modify calibration factors that are stored in the sensor when it's calibrated. This is recommended only for advanced users who are familiar with that function and have a particular need to use it. Response, similarly, allows the user to adjust the factors that are involved in the response time speed-up algorithm. Line frequency, you would set to 50 Hz or 60 Hz, depending on the AC mains line frequency in the country where you're located. And channel information gives you information of the devices that are now connected. We're now going to look at some of the special functions that are available. Sometimes we want to not only get a reading, but also to perform additional processing on the reading. The special functions are available by opening up this screen over here. Let's have a look at the functions that are available in this case. Average is used to deal with situations where we have perhaps an unstable laser or otherwise jumpy readings which are difficult to use. By selecting average, we can have the STARLAB application show us not the moment-by-moment real-time value, but rather a running average calculated over the particular time that we've selected. And that smooths out any possible jumpiness in the readings. Offset allows us to subtract out any constant background light level. For example, if we're measuring low power lasers in a room where there is background light that could affect the reading, we could temporarily block the laser, and then when we click offset, we will, from all further measurements, we'll subtract the background light until we deselect offset. Scale factor. If we're taking readings at various points in an optical setup, for example, the power coming out of the laser, and then the power after, for example, some attenuation factor, a filter, a beam splitter. We can place the sensor here, we could, after the filter, we could manually enter in the attenuation value, and then although the sensor physically is measuring the power after the filter, we can have STARLAB display for us the calculated power before the filter. And then when we deselect scale factor, it'll go back to displaying the actual real-time power that's being physically measured. Selecting dBm would display the power in units of dBm in applications where that's necessary. For example, in telecom applications or other uses of fibers. Deselecting it brings us back to power in units of, in this case, microwatts. The normalize function would be used in cases, again, where we need to take measurements at several different locations as a ratio of the power measured at some reference location. So for example, we could measure the power coming out of a source, select normalize, and then all subsequent measurements would be displayed as a ratio relative to the value at that reference source. Whenever we click on this arrow, we reset the reference value to what the power is at that particular moment. When we deselect normalize, we go back to measurement in absolute terms. Density would be selected if we need to measure not the absolute power in units of microwatts, but rather the power density in units, for example, of microwatts per square centimeter. When we select density, We then have to manually enter the spot diameter, and we get the power displayed as power density, microwatts per square centimeter. Here is where we would manually enter the number. And if we have a rectangular spot rather than a round spot, then we're prompted to enter the height and the width rather than the diameter. We're now going to look at using STARLAB with a pyroelectric sensor to measure energy per pulse of a repetitively pulsed beam. We again double-click on the STARLAB icon. And we've come to the Select Devices window. This time we're going to select the pyroelectric sensor, which in this case is sensor number 2. The pulsar can have up to 4 sensors connected to it. And again, to keep things simple, we're going to select Together. We click Together and we come to the main measurement screen. As we mentioned in an earlier segment, the parameters that come up on the main measurement screen are a function of the definitions available for the different sensor types. Here's the numerical readout, which shows us the energy reading, in this case in units of millijoules. Again, we have the graphical output. And here we have the measurement parameters of the sensor that the user can choose from. In this case, we're measuring energy. A pyroelectric sensor can also measure average power. We're going to leave it on energy. Here is where the user would select the wavelength, the energy range or scale. If we were using a pyroelectric sensor that has a removable diffuser, the user would here select whether he's using diffuser in or diffuser out. In this case, that's not the situation, so that parameter is not active. The user can select the maximum pulse width. In this case, it's either 1 millisecond or 10 milliseconds. I should mention that with most of our newer pyroelectric sensors from what we call the Pyro-C line, in a number of our instruments there would be up to 5 selections offered for maximum pulse width. In this case, the instrument that we're using, the pulsar, is offering 2 selections to the user. External trigger on or off is a function that we're going to be looking at a little bit later. That's a special feature that's available using the pulsar instrument. If we were to change any of these parameters, the Save button would become active and the user would be prompted, if he so chooses, to save those selections to become the default selections programmed into that sensor. Here we have statistical information about the measurement as it's been performed up until now, the minimum and maximum energies that have been recorded, their average, the standard deviation, the number of overranges, if any, the total number of pulses counted during the course of this measurement, and the pulse frequency. The missing pulses is not active right now. That goes back to the external trigger, which is a function that's used for detecting missing pulses, among other things. And as I said, we will be looking at that in a separate video segment. Here we have the graphical display. And again, we can adjust the X or time axis and the Y or energy axis. The time axis, let's bring that down to 1 minute so that it moves a little bit more comfortably, more quickly for our purposes. The Y-axis, we can adjust using the manual sliders or by typing in a value over here. That would normally be based on the average and max and min measurements that we see in the statistics window. And we would set the appropriate scale. We have, again, various graph types. Now we're looking at a line graph. We could convert that to a bar chart, a histogram, a pulse chart, or a virtual analog needle. Different selections of graph type might be more or less relevant depending on the type of sensor being used and the type of measurement being performed. For illustration purposes, we're going to leave it for now on a line graph. STARLAB enables us to record or log measured data for further analysis or even just for record keeping. Let's look at how we perform data logging. We first go to the log setup icon. When we click on that, we come to the log settings window. The default selection is to log one screen of data, which in our case, looking at the value of the time axis that we've chosen, would mean 1 minute of data. If we deselect that, other options become available. We could set it up to log and then stop after a preset timeout period or after a preset number of measurements. We're going to leave it on logging one screen of data. By opening the Browse button, we would select where the recorded log file will be stored. To begin the log, we press what looks like a play button, the Start Log, and the progress window shows us the progress of the logging as it takes place. We can stop the log early if we choose. It tells us where the file was saved to. The stopping the log does not interfere with the graphical output, but it does stop the process of recording the data. We can click on the Log File Location button, and then we can open up one of the log files, and it opens up by default as a text file. And here we see the information about the logging that took place, the settings that were used, the statistical information, and the data points, each with their timestamp. If we select Log Notes, we will be able to add text notes to a log file. For example, experiment number 3, date, etc. We can view the file by clicking on File, Open, and double-clicking on the file. That file opens and shows us graphically the data that was recorded. Of course, we cannot change measurement parameters because we're looking at data that was recorded from a measurement that has already taken place. But we can adjust how we look at this data by changing the X and Y axes or the graph type. We can also, by left-clicking and dragging, zoom in on an area of interest. If we left-click and drag anywhere in the reverse direction, it takes us back to the original graph position. We exit out from here, not from here, that would close the application, but from here, that closes a log file and returns us to the main measurement screen. We can also open up a file in text format by clicking Open File as Text. When we do that, the file opens up as a text file, exactly as we saw previously. The data can also be viewed in other formats, for example, in Excel format. In order to do that, we would have to log the file in an Excel-friendly format. We would do that by going to Options, Preferences, Logging, and then select Excel-friendly format as opposed to standard format. Opening a file in Excel would enable us to make use of the calculation and other functions that are available using Excel or other applications. If we were connected to an instrument such as the Vega or Nova 2, which have onboard data logging capability, then we would be able to upload instrument files. Right now that is not offered, but if we were connected to such a device, this icon would be active, and we could then go into the instrument's data file area and upload the appropriate logged data file and display it in the STARLAB application. There are just a few advanced functions that we're going to briefly look at. We've looked at zeroing, calibrate, line frequency in a previous video segment. Turbo mode enables us to make full use of the power of the instrument and record pulses at the maximum pulse repetition rate that's being measured by the sensor, as opposed to sampling the pulses at a lower frequency. We're now going to look at how to use multiple sensors or channels connected in parallel using STARLAB. We double-click on the STARLAB icon to open the application. And this time we're going to select both sensors that are connected to the pulsar. We can do that either by clicking on each box individually or by selecting pulsar. All the sensors that are connected to the pulsar are selected automatically. we're going to use together, which means that the time axis will be common for all channels. And now we're in the main measurement screen. We now see that there are 2 channels instead of only 1. Each channel is represented by a different color. The numerical readout window shows us the real time, in this case power, being measured by the active channel. Channel A is a thermal sensor measuring power. Channel B is a pyroelectric sensor measuring, in this case, energy per pulse. We select the first channel, which, as we just said, is the thermal, and we can adjust the axes of the graphical readout to appropriate levels to be able to comfortably see that channel. We adjust that to a value that allows us to easily see the information, either by using the slide switch or by manually typing in a number. We will again bring the time axis down to a level that's more comfortable for our present purposes. In this case, 1 minute for a full screen. If we select split, each channel is now shown in a separate window. The time axis is still common to both windows, but the y-axis, energy or power, is not common and can be adjusted separately. When we select merge, they come back together into one window again. In addition to measuring, displaying, and logging data from multiple channels, including the basic functions for optimizing the measurements, STARLAB enables you to perform various mathematical functions involving the different channels, such as ratio of one channel to another, or even user-defined functions. We do this as follows. We can also add a user-defined function. We call this a math channel. We're now going to see how that's used. We click on Add Math Channel, and we now create a third channel which will be displayed just as if it were another channel, such as the 2 sensors are each forming. These math channels, we can create any number of them. Their letters begin with M, subsequent channels would be named N, O, etc. The default function that comes up is the ratio of A over B. We can change that to pretty much anything we need. We can also create our own channel by manually typing in pretty much anything that we're required to do depending on what our application needs. If we X that out, then it disappears and we're back to just the 2 sensors that we started off with. We can perform logging of multiple channels, including a math channel if we have one open. The logging is done in the same way. We would use the log settings window to set up the parameters of the log and set the location at which the file will be recorded. And then we perform the log in the same way as before. We click on Start. The logging is in progress and we can follow the progress on the progress window. We can stop it early if we choose to. And we would open the file. And here we can see 2 different channels displayed on the logged data. And if we were to open that as text, we would see that as 2 separate columns of information, each with their timestamps. Here we see channel A and channel B, each with the appropriate timestamp. And the various channels are synchronized with each other in terms of the timestamp so that the user can know which data point corresponds to which data point among the various channels. We can save an overall measurement configuration before we leave the application so that it comes up as a default next time we open the application by choosing Options, Preferences, and Open Last Configuration. Now, when we close the application and reopen it, it'll skip the Select Devices window and go directly to the configuration that we set already as the default.